Hi, welcome to our lecture from Chapter 12 on atomic structure and the elements. The mystery of the structure of the atom was solved by using a science called spectroscopy. Spectroscopy is the study of atoms and molecules by analyzing the spectrum of light emitted by the atom. And this spectrum is called the atomic spectrum. So there are a couple different ways we can produce a spectrum. The first one is basically we take a sample of the atom that we want to analyze, and it's usually in gas form. And this gas is excited, and it can be excited by heating the gas, giving it energy, or by even using electricity to excite the gas atoms or molecules. And the gas then will actually produce light. It will glow. So this light is sent through a prism. And remember, one of the properties of light is when light goes through a prism, it undergoes dispersion, where the different colors and wavelengths of light bend at different angles, producing a spectrum of the light. So in other words, the light coming in is separated into all of its component colors. So these different colors that come out of the prism here this is called the spectrum of this particular gas. And this spectrum is usually shined on a screen, for example, or it is shined against something where we can measure where the different colors fall and figure out the wavelengths. Now, the prism is usually not used, but it's kind of easy to sort of visualize what's going on there. More often, the second method is used where instead of a prism, the only difference here is the light from, here's our excited sample of gas again. So the light is sent through something called a diffraction grating. And this will be explained in the video we're going to watch. But basically the diffraction grating acts just like a prism, and its job is to separate the light into the various colors that are comprise the light coming out of the gas. And again, this separation of colors is called the spectrum of the light. So let's go ahead and watch a video demonstration from another instructor, and he will explain what the diffraction grating is and also show you some examples of different spectra from different materials, including a solid metal filament in a light bulb, and also some different types of gas.
So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating, just like a street grate. It has lines through it, and this allows you to resolve the spectrum of a source of light in the same way that a prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with the diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present in this. So this is hydrogen. It has a reddish cast to it, and when the diffraction grating is in place, you'll see three lines. Those lines are associated with transitions of the electron in the hydrogen atom from a higher state to a lower state. So this is a mercury spectrum without the diffraction grating. And let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. That's nitrogen. This is neon. There's a beautiful orange look to it, and when the diffraction grating is in place, you see a large number of red and orange lines. This is exactly what's used for neon lights. The original neon light was made out of neon like this. There are other gases that are used to form signs, but neon was really where it started off. It has a beautiful, bright, reddish-orange spectrum.
In the video that you just watched, we saw a couple of different types of spectra that are produced. The first one was when the instructor had a light bulb. And an incandescent light bulb is it has a filament, which is a wire, and electric current passes through it until it heats up and it glows and it gives off light. And we saw that hot light bulb filament produced what was called a continuous spectrum. In other words, it looked like a rainbow with all the colors. But then he went ahead and looked at the spectrum of different gases, hydrogen, mercury, neon, etc. And we saw a very different result. Instead of a continuous spectrum, we saw 2, 3, sometimes more distinct bright lines that were associated with different colors, but in between the lines there was nothing. So this is called a distinct or discrete emission spectrum. Now, this was not explained by the physics of the early 1900s, so this became a mystery. Why does one material, the metal here, produce a continuous spectrum, and why does a gas produce the discrete spectral lines shown here? So this puzzle actually started a revolution in physics and would eventually lead to solving the mystery of atomic structure. Trying to explain the spectral lines seen in gases led to the birth of a new branch of physics called quantum physics, right around the year 1900. In this year, a physicist named Max Planck suggested that energies at the atomic level are not continuous but quantized in lumps. So this is where the word quantum comes from in quantum physics. So to kind of understand what this all means, let's look at an analogy here. In classical physics, the type of physics we've been talking about in this course, the energy of a system or an object is considered continuous. In other words, if we have an object like a ball or something like that, we can put it on a ramp like this. And of course, this ball has potential energy because it's raised some height h off the ground. So this ball can be anywhere on the ramp, meaning its potential energy, remember, is equal to mgh, can have any value. In other words, it's a continuous spectrum of energies here. But what Max Planck said is that down at the atomic level, this is not true. In fact, at the atomic level, Planck suggested that the energy levels are like stair steps, in that if we had an object, now this wouldn't be a ball, this would be something like an atom or even an electron in an atom. That electron would be sitting on one of these steps. And just like a regular stair step, we can't be in between two steps. We're either on this step or this step, or this step, etc. So the potential energy here in this case has discrete values. In other words, it's not a continuous spectrum of energies anymore. And by the way, the step height here is called one quantum of energy. So in other words, this object here can jump from energy to energy, but it can't be anything in between these steps. So Planck's hypothesis turned out to be true. It was later verified by experimental evidence. And this new idea started a revolution in physics, and many more ideas were to follow. We actually learned about Einstein in a previous chapter where we talked about light. And you may recall that Einstein sort of discovered this concept of what we call the photon. And so this is a few years after Max Planck's hypothesis. So Einstein was, inspired by what Planck found. And Einstein proposed that light waves also exist as tiny bundles of energy called photons. So you can remember in the last chapter, we talked about a photon. You can think of it as this little bundle or packet of, this is called a wave packet. And this is electromagnetic energy or light, but it's in this little discrete bundle of energy. So Einstein's photon model of light says that a photon is a particle of light, a tiny massless packet of energy that travels at the speed of light. Remember, the speed of light, c, is equal to 3 times 10 to the 8th meters per second. Furthermore, Einstein said that the energy of a photon is equal to h times f. Now, f is the frequency of the light, and h is called Planck's constant, and this is named after Max Planck. So Planck's constant, notice it has an extremely tiny value. It's 6.63 times 10 to the minus 34 joule seconds. So this is why no one had ever noticed those stair steps in energy like we talked about on the last slide. This Planck's constant is so tiny that for all practical purposes, the energy spectrum is usually seen as a continuous spectrum of energies. But down at the atomic level, this can become quite significant, and we'll explore that in this chapter. There's another value here for Planck's constant, which we will talk about later. It has different units that will be more practical for our use. And remember, Einstein also said that a light wave is a superposition, meaning you have a bunch of photons all with the same frequency, all traveling together at the speed of light. Okay, so just to kind of recap, in 1900, Max Planck suggested that energy is quantized, in other words, comes in discrete steps. And a few years later, Einstein said that the same holds true for light. Light energy is quantized into little bundles of light called photons. So putting these ideas together, in 1913, the great Danish physicist Niels Bohr combined these two ideas, and he put them together into a model that could explain the atomic spectrum of hydrogen. And so this is called the Bohr model of the atom. And Bohr won the Nobel Prize for developing this model. This was the first successful explanation of the atomic spectrum that was seen for hydrogen. So this is the Bohr model. It's actually fairly simple. This is for the atom hydrogen. Now, hydrogen is the simplest atom. It has a single proton for the nucleus in the center. All right, that's this little red ball here with the positive sign, because remember, a proton has a positive charge. And then there's one electron. All right, so the hydrogen has one proton and one electron. The electron has a negative charge. Now, here's the beauty of Bohr's model. Bohr said that the energy of this electron has to be in one of these steps. And these steps are usually drawn as orbits around the nucleus in the center. So here is the first orbit. This is the lowest energy level, n equal 1. The electron, if it's down here, this is the bottom step for the energy of the hydrogen atom. It can't go any lower than that, all right? And then the next step up is n equal 2, this level right here. So this is like kind of like the second orbit here. The next level up from that is n equal 3, where I have shown the electron in this picture. And then, you know, the one above that would be n equal 4. That would be the fourth step or fourth energy level. And it actually keeps going past that. So what Bohr proposed is that the electron has to be on one of these steps, just like our staircase example, right? If you have a ball on a set of stairs, the ball has to be sitting on one of the steps. It can't be in between a step. The same thing holds for the electron. The electron must be on one of these energy levels here, designated by n equal 1, 2, 3, 4, etc. Now, the real key to Bohr's model is how does it predict the emission of light and explain the spectrum? Well, this is where Bohr's model really becomes useful and powerful. Let's look at a process called photon emission. This says that if an electron jumps down to a lower energy level, it must give up this energy. So how does it do this? Well, it creates a photon of light to carry away the excess energy. So let's look at an example here. So here again is our Bohr model of the atom. The little green dot in the center, that represents the nucleus or the proton of the hydrogen atom. And then we see these energy levels. The first level, which I call E1 or n equal 1, is in here. The second level, E2, is right here, and we'll just draw 3 levels in this picture. Here's the third one here. So let's say our electron starts here in the third level. This electron can jump down to a lower energy level. But remember, when something goes from high energy to low energy, we have to get rid of that energy somehow. And remember that energy is conserved. It can't be created or destroyed. So if the electron is going to go from high energy here to lower energy here, it has to get rid of some energy. Okay, it can't, you know, this energy can't just vanish. So how does the electron do this? Well, this is the real beauty and you know, magic of Bohr's model. This is how photons are created. A photon of light is emitted by the atom to remove the excess energy. All right, and we're not, in this course, we're not going to explain the details of this process because it's a bit complicated how an electron jumping from here to here can produce a photon. But we actually have the scientific theory to explain precisely how this photon is produced. But all we need to know is that when the electron jumps from high step down to a lower step, it has to release that energy. So the photon energy is equal to the difference between E3 and E2. In other words, we take its energy at E3 minus its energy here at E2, and that's the difference in energy between these two levels. That must be the energy of the photon. And remember, that energy difference is equal to HF. This was Einstein's theory of the photon, where he says that the photon energy is equal to Planck's constant h times the frequency of the light, f. So the idea here of photon emission, and remember, you know, emission means giving something off. So this is how an atom produces a photon. This is how atoms produce light. And so again, this is an incredible sort of revelation to learn how light is produced. It's produced by the transition of an electron inside an atom jumping down to a lower energy level. We actually produce light in this manner. Now, one thing about the different energy photons. So depending on the step here, that's going to determine the frequency of the photon, and the frequency of light determines the color of the light. So this is why we see different color spectral lines. For example, remember in the hydrogen we saw a red, sort of a teal or greenish color, and a blue line. Those are due to the different jumps in energy as electrons jump back and forth between these energy levels. The converse process to photon emission is called photon absorption. This says that if an incoming photon has the proper energy equal to the exact energy difference between energy levels, the electron will absorb the photon and jump up to the higher energy level. So to see how this works, here again is our picture of our Bohr model. Here's the nucleus, and these are all the energy steps. So let's say our electron just happens to be sitting in n equal 2, the second energy level. Along comes this photon, and the energy of this photon is exactly equal to the difference in energy between the second energy level and the third energy level. So what this electron does now is it basically absorbs this photon. It's like the electron is hungry for energy, so it eats this photon, but now the electron has more energy. So the electron has to jump up to this next energy level. So this is how light is absorbed in different materials. The photons are absorbed by electrons, and the electrons jump up to higher energy levels. Now, what would happen if the photon's energy isn't the right amount? Well, what happens here is there's no absorption. In other words, the electron here is a very finicky, picky eater. It only wants to eat photons that have the exact amount of energy necessary to let it jump up to one of these other levels. If the photon has a different amount of energy, then this photon will just pass right through the atom, and this is what makes atoms transparent. For example, the atoms in our atmosphere are basically transparent to visible light, and that's why we can't see the air. So let's now go back to sort of a summary of the different atomic spectra that we saw in the video, and there might be a couple extra shown here. So this is just a small piece of a atomic spectra chart that might show dozens of different spectra. But these are, let's take a look at some of these spectra. This is hydrogen, and we saw in the video that hydrogen has a red line, and then it has a sort of a bright bluish green line, and then we were able to see, I believe it was this blue line here. Hydrogen, you can see, also has some more lines in the violet part of the spectrum. These were more difficult to see in the setup that the instructor used. But look at, here's sodium. Sodium has a completely different spectrum. Notice it's dominated by two yellow lines that are very close together. Helium, all right, is different from hydrogen and sodium. All right, it has a red, a yellow, and a few kind of blue-green ones here, and so on. And we also saw in the video neon, which had a whole bunch of red, orange and yellow lines that made it very bright with that color. And then I believe we also looked at the spectrum of mercury. So the point here is that every element has its own unique spectrum, just like a fingerprint. So no two elements have the same atomic spectrum. So this makes it extremely useful for identifying the composition of unknown substances. And you may have seen this in some of the CSI shows where they find some evidence from a crime scene, and it might be a little chunk of material stuck on the bottom of someone's shoe or something like this, and they send it to the lab, and they can determine exactly what the chemical compounds are that are in that little speck of material. And that you may think, wow, that sounds kind of like science fiction to me, but it's not. Spectroscopy is a very well-known and well-studied and extremely useful analytical technique to identify compounds in substance. Because remember, again, every single element, all right, all 90-some elements on the periodic table, they each have their own unique fingerprint called an atomic spectrum. And in astronomy, spectroscopy is extremely important because we can actually look at a distant star in a telescope and send that light from the telescope through a spectroscope or a spectrograph and analyze the spectrum of that star from a distance, and we can tell precisely what that star is made of. We can tell what elements are in that star and in what fraction, of the star is hydrogen, what fraction is helium, how much oxygen and magnesium does the star made of. So spectroscopy is a very powerful analytical technique that is used in many different branches of science. Let's look at some examples of atomic emission. One of them in astronomy is called a nebula, and a nebula just means a glowing cloud of gas. So this beautiful picture here is a picture of what's called the Lagoon Nebula. It's in the constellation of Sagittarius. And this is basically a giant glowing cloud of mostly hydrogen gas. There are other elements in it, and we can also see some dust clouds, these dark features here, but the predominant composition of this cloud from our study of spectroscopy is hydrogen. And we can sort of see this this is the spectrum of hydrogen here. Remember, there's a red line, sort of a teal colored line, and then some blue and violet lines. And if you blend all of these colors together, which is what our eyes see without a spectrograph, then we sort of see this purplish pink color from blending red and blue and purple, violet colors all together. So this, in astronomy, whenever we see a red, kind of a reddish, pinkish cloud like this, we know that we're looking at hydrogen. So this, and by the way, this nebula here is the birthplace of new stars. These stars inside the nebula here that you can see are actually newborn stars that have formed from this glowing cloud of just a giant cloud of hydrogen gas. Here's another interesting example of atomic emission. These are called the northern lights, or the aurora borealis, and these are seen in the northern and southern latitudes on Earth. What's happening here is molecules in the upper atmosphere are excited by collisions with solar wind particles that come from the sun. And we'll look at this in a little more detail later in the course when we study the sun. But for now, we can just see this glowing, kind of shimmering effect high up in the atmosphere. And again, this is caused by the oxygen and nitrogen atoms, or molecules in our atmosphere, glowing. And they're giving off an atomic emission spectrum, basically. And this is the spectrum here of nitrogen, and this is the spectrum of oxygen. And we're seeing mostly the green here from the oxygen, but you can see a little bit of the blue there that comes from the nitrogen, and maybe even some of the reds that come from both the nitrogen and the oxygen. Again, the process here is that these atoms or molecules in the upper atmosphere have been excited, and those electrons are going to be jumping down to lower energy levels within the atom. And when they do that, remember, they have to produce a photon of light. And so this is the light that we actually see here. Another example of atomic emission is the different colors that various flames have depending on the chemical that's burning. So there are a couple factors that affect flame colors. One is the temperature of the flame, but the other one is the chemical, and these are due to the different emission lines. So for example, here's a flame of lithium burning. Here's sodium, and here's potassium. If you remember back from the spectrum chart a couple slides ago, sodium had the two yellow emission lines, and so that's producing this dominant yellow color here. And by the way, fireworks here also, the colors that you see in fireworks are due to different chemical emission lines. This is an interesting image here. This is the spectrum of our sun. And the spectrum is so rich with information and different spectral lines that what they've done here is they've cut it into a bunch of stripes. So every one of these stripes or rows in this picture is just a little section of the entire spectrum. So if you cut all these out, imagine cutting every one of these little stripes out with the scissors and taping them all together end to end. I mean, it would be huge, right? This would probably, go all the way across your house. But within this spectrum here, these dark lines represent absorption lines, and we'll talk about this later in the course when we talk about astronomy. But for now, the absorption lines are associated where the emission lines would be. These have to do with different energy levels for all of the different elements that exist in the sun. So by analyzing this very complicated spectrum, and notice it has many thousands of spectral lines in here. All these little dark notches represent one jump from an electron in one type of atom. So over 65 elements have been identified from the spectrum. So what that tells us is that our sun is made up of quite a few of the elements. In fact, almost all of the elements in the periodic table exist inside the sun. Earlier in this course, we studied energy. And for the study of energy, we used the unit of joules for our energy units. And that was very practical for dealing with things like rocks and balls and, people going upstairs and things like that. But when we're dealing with atomic energy levels, the joule is not very practical because the energy levels at the atomic level are very, very tiny. So we're going to use a different unit of energy called the electron volt. So the electron volt, or EV, is a tiny unit of energy that's more practical for measuring atomic energies compared to the joule. So one EV, one electron volt, is equal to 1.6 times 10 to the minus 19 joules. So you can see that an EV is an extremely tiny little amount of energy. But this is going to be much more convenient when we study the atom. So remember that Einstein told us that the energy of a photon, E, is equal to hf. So, and h, remember, is called Planck's constant. But Planck's constant has two values. One is for joules and the other is for electron volts. So we're going to use the electron volt version of Planck's constant. So for our calculations, h is equal to this number here, 4.136 times 10 to the minus 15 electron volts per hertz. And this will become clearer when we go through an example next. So as an example, determine the energy of a single photon of light that has the frequency of 5 times 10 to the 14th hertz. So using our formula here, energy of a photon is equal to hf. H is this number right here, 4.136 times 10 to the minus 15 EV per hertz, and we multiply it by F, which is the frequency in hertz, which is 5 times 10 to the 14 hertz. So look what happens. The hertz here cancels the hertz here, and we're left with our electron volts. And notice the answer here is about 2 electron volts, 2.07 electron volts. And this is typical for the energy of a photon of light. It usually is, just a few electron volts. And that's why we use, one of the reasons why we use EVs instead of joules. Let's now work through an example using an energy level diagram that has to do with an electron transition. So in this example, we're going to determine the energy, frequency, wavelength, and color of light emitted during the electron transition shown. So let's take a look at this diagram that's given to us. So this is similar to the Bohr model of the atom. These levels here, these lines, represent the different energy levels for this. This could be an atom, okay? And so this is our lowest energy level down here. You can see it's labeled at 1 electron volt. The second level is labeled 2 electron volts. This one, 4 electron volts, and the top level is 7 electron volts. And what this diagram shows is there's an arrow going from the 4th level down to the 3rd level, and this red dot right here, this represents our electron. So this is an electron transition or change from E4 down to E3. And we know when an electron jumps down, it has to emit a photon. So this, this little squiggly line here, this is our wave packet that represents a photon being emitted by this transition here. Okay, so this is just a little different way of looking at the Bohr model of photon emission, which we've been talking about. So the first thing we're going to do is figure out, the energy of our photon. Well, to figure out the energy of the photon, that's actually very easy, because look, the electron started up here at 7 electron volts, and it ended up at 4 electron volts. So to go from 7 to 4, the photon must carry away 3 electron volts. So we just take 7 minus 4, which is 3 electron volts. Now, what is the frequency of this photon, of this light? Well, here we can use Einstein's formula, E equals hf. So F equals E over h. The E is 3 electron volts, and h, remember that's Planck's constant. We're going to use the one in eV units from the last slide. So it's 4.136 times 10 to the minus 15. So that's down here. So 3 divided by that number gives us the frequency, which is 7.2 times 10 to the 14 hertz. And, this reminds us again that the frequency of light is extremely high. This is 720 trillion hertz. Okay, so it's light vibrates very, very quickly. Okay, so we've got the frequency. The next thing is to determine the wavelength of the light. So for wavelength, remember that we have the speed of a wave, v, is equal to wavelength, lambda, times frequency, f. So let's solve this for lambda, the wavelength. Wavelength equals v over f. But remember, the speed of a photon is the speed of light, c. So I'm going to replace this v with a c. And of course, c, the speed of light, is 3 times 10 to the 8th meters per second. The frequency f, we're going to use our number right here from this last step, 7.2 times 10 to the 14th. So when we divide this number by this number on our calculator, being careful to use scientific notation here, we get our answer in meters, 4.2 times 10 to the minus 7 meters. And what I've done here is I've converted this to nanometers. Remember, there are 1 billion nanometers in 1 meter. So basically, we multiply this times 10 to the 9th power to convert it to nanometers, and we get 420 nanometers. Now, so that's our wavelength, 420 nanometers. The last part here was, what color is this light? Well, for here, I have to look on an electromagnetic spectrum for visible light. 420 would be somewhere right around here on this spectrum. Here's 400, here's 500. And so that would fall in the violet part of the spectrum, meaning that this transition up here is going to produce violet or purple light. So the work of Max Planck and Einstein and Bohr started basically unraveling the mystery of atomic structure. And within the next several years, the structure of all the atoms was determined and figured out. And basically for all the atoms, the structure is shown in this model here. In the center of the atom is what's called the nucleus. And the nucleus contains neutrons and protons. And the protons are positively charged particles, and the neutrons are neutral. They have no charge. That's why they're called neutrons. And by the way, we are going to study the properties of the atomic nucleus in the next chapter. That will be the topic of our next chapter in the course is nuclear physics. Around this nucleus is a cloud of negatively charged electrons. And you can think of these electrons as just swarming around, or you can think of them as orbiting around the nucleus. That's not precisely correct, but it gives us a nice picture to at least kind of get a simple understanding of how to think about what an atom actually looks like or how it's built. Most atoms are neutral in that they have the same number of protons as electrons. So in this example here, we have 7 protons inside here. Therefore, we have 7 electrons in the cloud of electrons. Now, why do these electrons stay in the atom? Why don't they just go flying off into space? Well, the electrons are negative charge, and they're attracted to the protons. So these electrons are, you can think of them sort of in orbit around this nucleus. This leads us to what is called the shell model of an atom. And the shell model basically tells us about how the electrons in an atom are distributed in energy. So these two pictures here, this is sort of a three-dimensional picture. It sort of looks like layers of an onion. And down here, remember, in the very middle of the atom is the tiny little nucleus. Okay, here it is in this picture over here, where we've just sliced the atom in half. These shells around the nucleus, these circles, they represent different energy shells. And these numbers tell us how many electrons can fit in each one of these shells. So one way to sort of visualize this is it's almost like a movie theater where, you know, here's the stage or the screen up in front in the center. And this first row of seats, there are only 2 seats, meaning only 2 electrons can sit there. The next row has 8 seats. You can put 8 electrons in this row or in this energy level. The third energy level also has 8 seats. And then the next row has 18, then 18, 32, and 32. And, you know, remember this whole thing is three-dimensional, more like this. So the way this works is for any atom, depending on how many electrons it has, the electrons will all try to crowd and get as close to the center as they can. Just like in a movie theater, you know, you'd maybe want to sit closer up front. So these front rows will fill up first, and as we add more electrons, we keep filling up the farther rows, the ones that are higher and higher in energy, until, you know, we end up with so many electrons, some of the atoms, the electrons are actually out in this last row of 32 electrons. So we'll see how this works in the next few slides, but basically this idea of the shell model leads us to the periodic table of the elements. So to see how we can use this shell model to basically build up our periodic table of the elements, let's start with hydrogen. So hydrogen, remember, is very simple. It has 1 proton, and therefore it has 1 electron. So that 1 electron is going to sit in this first shell here. You know, remember there are 2 empty seats here, and we've got 1 electron, so it's going to go in this first row here. So this is hydrogen shown here. Now helium has 2 protons, therefore 2 electrons. But both of those electrons can fit in this first shell because there are 2 seats, you know, 2 available spots or energy states, they're called, for those electrons. So helium can be drawn like this. So the symbol, you know, we got the little red dot in the middle for the nucleus, which, by the way, just doesn't show all the protons. Okay, we're just going to use a red dot to indicate the nucleus. But you can see both electrons are shown as the little blue dots there, both in the first shell. So there, hydrogen and helium, that makes up our first shell because there are no more seats available. So now if we want to go to the next atom, we have to go to the next shell. So shell number 2, we can see in this picture here, holds 8 electrons. So the third element is lithium. Lithium has 3 protons, therefore 3 electrons. The first 2 electrons can go in the first shell because there's seats again for 2. The third electron has to be in the second shell out here. Okay, then beryllium is the next one. Beryllium has 4 electrons, 4 protons, 4 electrons. So 2 electrons in the inner shell, and then the other 2 electrons can go in the second shell. Boron, we add another electron. Carbon, add another electron. Now notice when we add electrons, there's still room in shell 2 because shell 2 can hold 8 different electrons. So when we get to nitrogen, oxygen, fluorine, finally, when we get over here to neon, all right, neon has 10 electrons. The first 2 go right here in the inner shell. The next 8 are going to all fit in the second shell here, and we've now filled up that shell because we've got 8 electrons in the second shell. So therefore, we're at the end of this row of the table. The next element, which is sodium, we have to add 1 more electron. And where does it go? Well, it can't fit in the second row or second shell because it's already full. So we start filling up the third shell now, which also holds 8. So that is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. And when we get to argon, we have filled up the third shell. So this process just keeps repeating for every element. We just keep adding 1 proton to the nucleus, and we add 1 electron to the shells, and we have to obey the seating constraints here due to the shell model being 2, 8, 8, 18, 18, 32, and 32. So when all is said and done, we have basically constructed the periodic table of the elements. So it looks like this, and it kind of has this weird shape because remember the first shell can only hold 2 electrons. So that's hydrogen here and helium here. The next shell holds 8. That was the lithium, beryllium, boron, carbon, etc. The third shell holds 8, sodium, magnesium, aluminum, and so forth. The next shell after that holds 18. So that's potassium, calcium, etc. All of these 18 elements here are filling up that 4th shell. The 5th shell also holds 18. So there are 18 more elements in this row here. Now here's where it gets kind of interesting. The next row, there are 32 available spots for electrons. So there should be 32 elements in this row. Well, actually there are, but they just don't fit. So the way they always draw this is look at the, before we explain this number up here is called the atomic number. And that tells us how many protons. So hydrogen has 1 proton, helium has 2 protons, lithium 3, beryllium 4. Here's oxygen has 8 protons, right? And then of course that letter there is called the chemical symbol. So let's go back down to this row that has 32 elements in it. So notice we start here with cesium 55, barium 56, lanthanum 57, but then look, it jumps to 72. So what happened to 58 through 71? Well, they're down here. So here's 58, 59, 60, all the way to 71, and then we go back up here to hafnium 72, tantalum 73, etc., tungsten 74, and the same thing for this last row here. Technically there could be 32, but we go from 87, 88, 89, here's 90 down here, 91, 92, going up to 103, and then we jump back here. So, the periodic table has kind of an unusual, quirky shape. It should be actually stretched out to 32 different columns, but in order to do that, it would be very difficult to put on one page. It would be so wide. So these extra elements are sort of placed down here. Anyway, this is the whole study of chemistry involves analyzing the periodic table in great detail. For example, all these different columns represent elements that have somewhat similar properties due to the position of the electrons in their shells. And you know, there are a bunch of features like that in the periodic table that we're not going to investigate in this course. But the one thing I will mention here is that all of the matter that we're made out of, you know, the earth is made out of, our bodies are made out of, everything, you know, our buildings and cars and everything, all those elements are found on the periodic table of the elements. And the only difference between these elements, remember, is the number of protons in the nucleus and the number of electrons orbiting around the outside. That determines the difference between the various elements. They're all made of the same three building blocks: protons, neutrons, and electrons. So how we arrange those three particles determines the difference between something like oxygen, cobalt, iron, or uranium. We can use the shell model to figure out the number of electrons that are in the outer shell. So to see this, let's look at an example. How many electrons are in the outer shell of chlorine? So chlorine has the symbol Cl, and if we look back on the periodic table of the elements on the last slide, we find out that the atomic number of chlorine is 17. Therefore, chlorine has 17 protons, and therefore it also has 17 electrons. So the question is, how are these 17 electrons distributed in the shells of chlorine? Well, remember the shell model has 2, 8, 8, 18, 18, 32, and 32 available seats or energy states for electrons. So chlorine, we just have to fit 17 electrons into these shells. So the first shell is going to have 2. The second shell is going to have 8. So that's a total of 10 electrons. So since chlorine has 17, we know there are 7 more. Well, all 7 of those electrons can fit in this third shell because it can hold 8. So the outer shell here of chlorine has 7 electrons in it. Let's do one more. How many electrons are in the outer shell of arsenic? So arsenic, symbol As, has an atomic number of 33, thus we have to fit 33 electrons into our shell model. So 33 electrons goes in 2 into the first shell, 8 into the second shell. The third shell also can hold 8. So 8 plus 8 plus 2 is 18. Well, we've got 33 we have to fit. So 33 minus 18, there are 15 more electrons that we have to fit in, and all 15 of those can fit in this fourth shell because it can hold 18. So our answer is there are 15 electrons in the outer shell of arsenic. We can use the idea of the periodic table and the shell model to also get sort of a feel for the relative sizes of the atoms. And so what this chart here shows is it's part of the periodic table, and each element is sort of depicted as a sphere that represents the relative size of the atom compared to its neighbors. And so one thing, there's 2 trends that we notice in this chart, 2 patterns. If we go down a column, notice the atoms or elements get bigger and bigger. So starting with hydrogen here, lithium is bigger, sodium is bigger yet, this is potassium is even bigger, and so forth. So, and we can do that over here too. If we go oxygen, sulfur, selenium, and tellurium, notice that the elements or the atoms get bigger as we go down. Now, why is that? Well, that's pretty easy to explain. As we go down, remember, we're adding another shell. So whenever we add a new shell, we're making the atom bigger. We're adding another layer of electrons to the outside of the atom. So that makes sense. But here's another trend that is a little less obvious. If we go across any one of the rows, we see that the atom starts big and it actually gets smaller as we go to the right in general. There are, a couple little exceptions here. The reason for that is that when we move across a row, we're adding more and more protons as we go across, and more protons cause a greater attraction to the electrons around them. So the shells are drawn closer to the nucleus. In other words, chlorine here, even though it has 3 shells, just like sodium, chlorine has more protons pulling those shells and squeezing them in tight due to the attraction between the protons and the electrons. So as we go across the column here, or I'm sorry, across the row, we see smaller and smaller atomic sizes. What are the actual sizes of atoms? Well, obviously, atoms are extremely tiny. We can't see them. In fact, even with our best microscopes, we really can't see an atom with light because atoms are as small as the light wavelength that we're trying to use to probe them. I will show you some pictures shortly using some imaging tricks where we can sort of get the sense of what atoms look like. But in terms of their scale, if we look at the smallest atom, which is hydrogen, the whole diameter, we got 1 proton here and 1 electron orbiting around. The whole diameter of this hydrogen atom, which is just 1 shell, is somewhere on the order of 2 times 10 to the minus 10 meters. And so obviously this is an extremely small number and an extremely tiny diameter or distance. If we look at one of the largest atoms, which is cesium, this has 6 shells. Well, you would think it would be a lot bigger than hydrogen, but it's actually not that much bigger because cesium has so many protons in here that it's pulling these shells in relatively tightly. So the size of the cesium atom is only about 5 times 10 to the minus 10 meters. So it's only 2 or 3 times larger than the hydrogen atom. Now, interestingly, the nucleus, as tiny as these atoms are, the nucleus is more than 50,000 times smaller than the atom itself. So in this picture here, I show the nucleus right here, but if I were to draw this nucleus to scale, the nucleus would be microscopic in this picture. It would be a tiny speck that you wouldn't even be able to see with your eyes because the nucleus is so tiny. And we will study the nucleus in the next chapter in detail. Here is our last slide of our chapter on atomic structure and the elements. These are some images made of atoms using a tool called a scanning tunneling microscope, or STM, and also another one is called an AFM, or atomic force microscope. These allow resolution down to single atoms. So here is a surface of a silicon crystal, and each of these little bright spots here represents the location of an individual silicon atom. This is a piece of gold, and again, each of these little dots here represents the position of a single gold atom. This is table salt, or sodium chloride. So here we have basically a molecular crystal, or an ionic crystal, where we have sodium and chlorine atoms. And this picture here is kind of interesting. These are oxygen molecules on an aluminum surface. So you can actually see in these molecules here, you can see the location of the 2 oxygen molecule atoms, bonded together to form an O2 molecule. So that is our discussion of atoms. I will see you soon for our next lecture, which will be on the atomic nucleus. Until then, goodbye.